Hi, I'm Mingquan and my talk is about distributed Laplacian solver and its applications in distributed graph problems. This is a joint work with Sebastian Forster, Gramoz Goranci, Yang Liu, Richard Peng, and Xiaorui. This talk has 4 parts. Firstly, I will give some background about the Laplacian matrix, Laplacian solver, congested model, and the distributed Laplacian solver. Then give our results on distributed Laplacian solver and its applications in several distributed graph problems. Next, I will present the related method, parallel Laplacian solver, proposed by Peng and others in 2016, and explain why this method cannot be efficiently implemented in congested model. To overcome this barrier, we proposed a new framework for Laplacian solver, which is specifies the Schur complement using Vertex Sparsifier and Schur complement Sparsifier. Alternatively, to make the computations efficient, we represent these two kinds of Sparsifiers as the minors of the communication network. Given a weighted graph G, each edge UV has a weight WUV. For the Laplacian matrix LG, the diagonal entry is equal to the summation of the weights of edges incident to this vertex, and the non-diagonal entry is equal to negative of the edge weight. A Laplacian solver is used to solve Laplacian linear systems, LGX equals B. Spellman and Teng gives the first near linear time algorithm. After that, Laplacian solver has given rise to some useful tools, such as ultra-sparsifier, spectral sparsification, and G-trace, and has been applied to many graph problems, such as max flow, bipattern matching, mean cost flow, and multi-commodity flow. It was also extended to other family of linear systems. For example, the connection Laplacians in the work of Peng and others in 2016. Given that the Laplacian solver has been applied in many sequential and parallel algorithms, in this work, we design a distributed Laplacian solver and use it as a primary tool to solve distributed graph problems. For the distributed settings, the congested model is employed. We use an undirected graph to represent a synchronized communication network. Each node represents a processor, and each edge represents a communication link between two processors. In each synchronized round, the two endpoints of each edge can exchange big O log n bit messages. In the congested model, the goal is to solve problems with a minimum number of communication rounds. In this work, we solve Laplacian linear systems, LGX equals B, in the congested model. Given a graph G and a vector B, each node I holds the scalar Bi and edge weights Wij, with J being incident to node I. And our goal is to compute the vector X with the minimum number of communication rounds. Here are our results. Given a weighted and undirected graph G and vector B on n vertices, we can solve the Laplacian linear systems, LGX equals B, approximately in the congested model, with big O n to little o1 square root n plus d rounds. We also give the lower bound big omega tilde square root n plus d for solving Laplacian solver in congested model. Our upper bound matches the lower bound up to a subpolynomial factor. Also, we give the m to 3/7 plus little o1 n to half d2 quarter plus d round algorithms in the congested model for the following problems. The first one is the exact max flow problem for directed graphs. We simulate matrix paper, which is based on the interior point method framework to give a distributed algorithm. Previously, Xiaorui and the others give an algorithm for max flow with n to little o1 square root n plus d rounds in the congested model. But their method only works for undirected graphs and gives an approximate solution. The second problem we solved is unit capacity mean cost flow. This algorithm is obtained by simulating the sequential algorithm for Cohen and others. The third one is shortest path with negative weights, and this problem can be reduced to mean cost flow problem. When the graph is sparse and the diameter is small, we are the first to give an little o(n) round algorithms for these three problems. To obtain the desired results, we use the concept of minors explicitly in the congested model. In the classical definition, graph H is a minor of graph G if H can be obtained by deleting or contracting edges of G. Equivalently, this means that vertices of H can be mapped to disjoint subsets of vertices of G, and each edge of H corresponds to an edge of G. Here is an example. H is a minor of G because the vertices 1, 2, 5 in H correspond to 1, 2, 5 in G respectively, and the vertex 4 in H corresponds to the vertex set 3, 4 in G. In this work, we extend the classic minor to the row minor. The differences of these two definitions have two aspects. Firstly, any two mapped subsets of vertices of G may have overlap. Secondly, each vertex and each edge of G are used at most row times. Here is an example. H is a 3 minor of G. Vertex 1 in H corresponds to the vertex set A, B, D, E in G. Vertex 2 corresponds to A, C, D, and vertex 3 corresponds to C, D, F, G. Here, the vertex D appears in 3 vertex subsets of G, so rho is equal to 3. Graph minor in our new definition has the composition property. If graph G1 is the row 1 minor of graph G2, and G2 is the row 2 minor of graph G3, then G1 is the row 1 times row 2 minor of G3. Another property will be used later is that in the congested model, if graph H is a row minor of the communication network, then distributed algorithms on H can be simulated in the communication network with the number of communication rounds being proportional to rho. Now I will briefly go over a related method to our work. The parallel Laplacian solver proposed by Peng and others in 2016. Given a Laplacian matrix LG with n vertices and a partition of vertices into two sets S and T, Cholesky factorization implies that if the inversions of the two smaller matrices, submatrix of LG on S and the Schur complement of LG on T, can be efficiently solved, then the pseudo-inverse of the entire matrix would be easy. Here, SCLGT represents the Schur complement of LG onto T, which is the resulted matrix by eliminating variables within the set S from the Laplacian matrix LG. Once the inversions of the two smaller matrices are obtained, we also need to multiply matrix Z and Z transpose. Here, matrix Z can be easily obtained by the inverse of submatrix LG on S. Based on Cholesky factorization, Peng and others compute the pseudo-inverse of the Laplacian matrix LG as follows. The initial step is to sparsify the graph H using a spectral sparsifier so that it can find an almost independent set of vertices S. Since the Laplacian matrix on an almost independent set is well approximated by its diagonal, it would be easy to compute the inverse of the submatrix LG on S. For the Schur complement of LG onto T, it computes a sparse graph H such that LH approximates the Schur complement of LG onto T. Such a graph H is called a vertex sparsifier. And then we repeat the steps 1 and 2 on graph H. Now I illustrate the above process. Let G1 be the graph G with n vertices. We do Cholesky factorization on G1 to get the result shown in the blue rectangle. Then compute a vertex sparsifier G2 such that LG2 approximates the Schur complement of LG1 onto T1. Then we do a Cholesky factorization on T2, whose result is shown in the second blue rectangle. Continue this process, we can obtain a vertex sparsifier chain G1, G2, and so on and so forth until the vertex set of the graph has a constant size. For graph GI, the size of SI is a constant factor of the number of vertices in GI. So the number of vertices in GI plus 1 reduces by a constant factor compared with GI. So the recursion would have depth big O log n, which implies a polylogarithmic depth parallel Laplacian solver. In the work of King and others, vertex sparsifier H satisfies that LH approximates the Schur complement of LG onto T. The problem is that although the approximation works in algebraic sense, the graph H is no longer a minor of the communication network because some edges are added. This prevents us implementing this parallel Laplacian solver directly in the CONGEST model. Look at this figure. Two edges 1, 6 and 2, 5 are added to H. Since there are no edges between them in the communication network, they use paths to send messages. Vertex 1 uses path 1, 3, 4, 5, 6 to send messages to vertex 6, and vertex 2 sends messages by path 2, 3, 4, 5. This may cause congestions on edges 3, 4, and 4, 5. Recall that in each round, each edge is allowed to propagate big O log n bit messages. So congestions on edges make the distributed algorithm inefficient. In order to resolve this issue, we utilize the random walk approach proposed by Durfee and others to construct a vertex sparsifier and implement that elaborately in the CONGEST model. This new vertex sparsifier approximates the Schur complement of LG onto T, and meanwhile is a log n to big O1 minor of G. However, now the problem becomes if we use the recursion with depth big O log n, it would result in a log n to big O log n minor of the original graph because of comparisons of minors. Recall that when graph H is the row minor of the communication network, the number of communication rounds taken by the distributed algorithms on H is proportional to rho. Here, rho is the log n to big O log n. The resulting number of rounds would have the factor log n to big O log n, which is not acceptable. For this problem, our strategy is early termination. That is, we set D to big O log n square. We expand this d rounds of the recursion from G1 to GD and combine these d approximate equations together to obtain a new approximation for LG pseudo-inverse with new matrix Z and vertex sets S and T. Our remaining task is to approximate the Schur complement of LG onto T using a different approach. Instead of directly approximating the Schur complement of LG onto T by the vertex Sparsifier, we use the Schur complement Sparsifier, firstly proposed by Li and Xiaorui in 2018. We use the vertex Sparsifier chain to obtain the set T and take advantage of the Schur complement Sparsifier to return a good minor H, satisfying that the Schur complement of LH onto T approximates the Schur complement of LG onto T. Now we implement the Schur complement Sparsifier in congested model. The work of Li and Xiaorui is a sequential algorithm for Schur complement Sparsifier. Each edge is contracted with probability being its Lagrange score or deleted otherwise. Contracting or deleting an edge would change the Lagrange scores of all the remaining edges. In order to avoid a lot of recomputation, instead of dealing with only one edge at a time, Li and Xiaorui sample random spanning trees from which one subset of tree edges is deleted and another subset of tree edges is contracted. However, sampling spanning trees of weighted graphs in congested model is hard. In our work, we compute the steady sets, which are a parallel version of the work of Li and Xiaorui. When we can implement a vertex Sparsifier chain and the Schur complement Sparsifier in the congested model, we combine these two tools together to give the whole flow chart. Initialize G1 with graph G. For graph GI, we apply vertex Sparsifier chain and obtain the terminal set TI. Then we use the Schur complement Sparsifier to get a graph GI plus 1, such that the Schur complement of LGI plus 1 onto GI approximates the Schur complement of LGI onto TI. Here, one point worth noting is that we can compute the pseudo-inverse of Schur complement of LGI plus 1 onto TI based on the pseudo-inverse of LGI plus 1. So the goal of a Schur complement Sparsifier is just to return the graph GI plus 1. In addition, the vertex Sparsifier chain and Schur complement Sparsifier of GI can make sure that the size of VGI plus 1 is a constant factor of the size of VGI. For GI plus 1, we do the same things to obtain GI plus 2. Continue this process, we can obtain a Schur complement chain, and each GI is an N2 later 01 minor of the original graph. By virtue of the Schur complement chain, we can solve the Laplacian linear systems LGX equals B in big O N2 little 1 square root N plus D rounds in the congested model. To sum up, in our work, we propose a distributed Laplacian solver in congested model with big O N2 little 1 square root N plus D rounds, which almost matches the lower bound, and we apply it to several distributed graph problems. In addition, we explicitly use the concept of minors, which can be taken as a general tool for other distributed problems. That's all. Thank you.